Nestled in the quiet outskirts of Ruston, Louisiana, Lincoln Parish Park is an ideal destination for residents looking for adventurous mountain bike trails, picturesque campgrounds, and pristine views of the nearby Hoogland Lake. To provide additional amenities to visitors, the park will be expanded to include a disc golf course that will feature a non-invasive man-made river to increase the variety of available obstacles. To accommodate the river crossing bisecting the disc golf course, as well as providing access for maintenance vehicles, the construction of a multimodal steel bridge has been proposed. Focus has been placed on preserving the natural ecology of Lincoln Parish Park through smart, rapid construction and providing a design that complements the park's inherent charm.
Before we begin, we would like to acknowledge that UBC Steel Bridge operates on the traditional, ancestral, and unceded territories of the Musqueam people. As a diverse and inclusive group of current undergraduates and alumni, we have worked together over the past year to deliver a robust and balanced design that best meets the needs of the community. To tackle the issue at hand, we have designed a symmetric 20-foot truss inspired by both Warren and Pratt trusses. The bridge consists of 55 steel members, 4 unique types of bolted connections, and weighs approximately 260 pounds. Under a dead load of 2,500 pounds, it is anticipated to have an aggregate deflection of 1 inch. This bridge can be constructed in 14 minutes with 3 builders.
Meeting client specifications, UBC Steel Bridge has been designing, modeling, fabricating, and constructing a balanced and optimized bridge solution.
Our design process begins with ideation of potential truss designs. Topology optimization using Altair Inspire was used to inform where materials should be located for optimal stiffness and to inspire overall bridge design. Members located at the end of the bridge were thickened to counteract large compressive forces, whereas the section sizes of the end deep chords were reduced due to lesser imposed axial force. Additionally, the stringer ends are extended rods for lightness and compliance with the rules. Deep truss diagonals were then optimized by simplifying the load path and maximizing member utilization. Ultimately, an iterative design process led to the bridge's unique trapezoidal shape.
Our bridge uses 4 types of joints: the U-joint, L-joint, imposter joint, and the X-joint. The U-joint and L-joints were designed to be lightweight and are frequently used in the bridge design as builders found these joints easier to connect.
Similarly, the wedge-like design of the imposter and axe joint is efficient for its constructability while also enabling compression in the upper chord, effectively locking and bearing onto one another.
Taking our preliminary design, a multifaceted approach was used to optimize our members. Altair S-frame modeling informed our decision-making, while capacity-to-demand ratios were verified using an Excel macro workbook where critical members were spot-checked by hand. The most extreme axial forces were then extracted from the S-frame model and used for capacity checks for each joint concept. The final S-frame model was then exported into a 2D layout on AutoCAD where a final joint placement and member design was determined. This 2D model was then used to create 3D parts and assemblies within Autodesk Inventor. In addition to producing fabrication drawings, the model was used to simulate construction using Navisworks, a BIM software. After team-wide reviews to ensure that the design complied and fit to given standards, shop drawings were drafted to facilitate external collaboration.
These drawings and 3D models are then sent to fabricators that laser cut, tube laser, water jet, and CNC the individual components of the bridge. CNC welding jigs were also produced. A particular innovation this year was the use of full-scale horizontal jigs, allowing us to lay out components of a single side of the bridge in its fully bolted configuration. This afforded us numerous advantages, chiefly minimizing any difficulty in complying with the required dimensions, and ensuring that each piece smoothly joined together during construction. We are able to achieve a lean, resource-efficient fabrication process through our partnership with local expertise and suppliers. Special thanks are extended to Nick Steel, our lead steel fabricator, as well as to Marco Metal Fab, Brenco, and Reliable Tube.
In pursuit of continued growth, UBC Steel Bridge added a new stage in our design cycle. Multidisciplinary members led weekly construction practices, beginning at conceptual design stages. This endeavor allowed the team to grow more familiar with competition rules and shifted our focus more towards a balanced bridge. Our findings deemed the barge necessary to reduce delays in connections at the midspan, allowing designers to ideate bridge shapes without the river construction limitation. Further advancement and refinement was explored through the use of tools, most notably full bridge height hangers, equipped with quick-release switches to allow the hangers to lengthen and detach. Builders gained the ability to construct the deep chord of the bridge without additional assistance.
Through our culture of interdisciplinary collaboration, from our community to yours, we have created an innovative and sustainable solution. Balancing construction speed, weight, aesthetics, and structural efficiency, UBC Steel Bridge has created a robust design that best meets community needs.